and welcome to my video for my lab 4 for Physics 2212. So for this lab, we're going to be observing interactions within a circuit. We're going to create and observe the interactions between batteries, capacitors, resistors, and light bulbs of varying potential difference and resistance. So for experiment 1, we found that the current remains constant in a circuit. In experiment 2, we found that the time necessary for a capacitor to charge increases with resistance. And then for 3, the natural log of the ratio of instantaneous change in potential difference to the overall change in potential difference will demonstrate a direct proportionality with change in time. So some fundamental concepts and equations are the node law, which says that the current in and out is equal in a closed circuit. The potential difference within a closed circuit is also 0. The given potential difference in a circuit is equal to the current times the resistance. The resistance of a voltmeter is assumed to be infinity, and the resistance of an ammeter is assumed to be 0. So for experiment 1, we're taking a wire, some batteries, some ammeters, some resistors, and a voltmeter, and we're creating a circuit with them. Everything else is in the surroundings, and because this is an online simulation, we're limiting external factors and forces. So initially, we set up the circuit you'll see on the next slide with two 1.5 volt batteries, 2 ammeters, and 2 resistors set to 47 and 100 ohms respectively. We recorded values, we reversed the ammeter and recorded that, and then we replaced ammeter 1 with the voltmeter. Circuit was reclosed and voltmeter took the readings across the circuit. And so you can see right here, we took out the ammeter. For the sake of the experiment, this is ammeter 1, and then this down here is ammeter 2. We take out the voltmeter right over here, and then here we're taking it and taking the voltage of the entire circuit. So the results initially, the current was equal to 0.02 amps. Reverse, the current remained the same. The voltmeter is that red for that. The voltage was 3 volts and the current was 0 because the circuit's been broken, so no charge is moving through the wire. When we connect it and reconnect the circuit, we reaffirm that the voltage is 3. And then we find these voltages around the resistors, and then the ammeter in parallel, it gives this current. And so this is an approximate graph. You can see that the slope here, it's a bit hard to tell, but it's a bit steeper because of the higher resistance. And then some calculations to calculate kind of just confirms the resistance that we set for the resistors, the potential difference over I, kind of from our V equals IR equation. We found each of these specific resistances. So for experiment 2, we took a 10 ohm light bulb, a 20 ohm light bulb, a 200 capacitor, MF capacitor, a 9 volt battery, and a stopwatch. Our system was a circuit, and the surroundings were everything else. We set up the circuit with the capacitor, the 10 ohm bulb, and the 9 volt battery. We removed the battery, and the effect of the capacitor alone was observed. The capacitor was then discharged. And then the experiment was redone with the stopwatch, measuring the total time taken. And then step 4 was repeated with the 20 ohm light bulb. And so the results that we found was that the charge is equal to 14.5 seconds and the discharge is equal to about 19.2. And then for the 20 ohm light bulb, the time to charge took about 30 seconds and the time to discharge took about 38. So for experiment 3, we are discharging a capacitor. So we took a 30 ohm light bulb, another 200 MF capacitor, a 9 volt battery, and another stopwatch. Our system was again the circuit, and the surroundings was everything else. So initially, the circuit was established with the battery, capacitor, and bulb, and then time was very slowly progressed to gather a set of data points measuring the voltage across the capacitor, and the values were recorded and further manipulated, and then we used these equations when plotting them against each other. And so here is just a quick Excel document that I whipped up for everything. You can see the first graph plotting the regular change in potential energy against time, and then when we take the natural log of the ratio, we're seeing a negative downward trend. And so to discuss a bit of error, there could be some random error in the experiment. There was human error in marking the change in time. I was the one stopping and starting the stopwatch in each experiment, so human error and time intervals cannot be ruled out, which would cause a slight shift in data points. And then systematically, there might be a rounding error in the instruments. In the FET simulation, the measure of the voltage dropped below 3 significant figures, but because of the FET simulation, the charges were unable to be accounted for, given the max number of significant figures on the voltmeter. And then what if a real ammeter was used in real life? So real ammeters don't have 0 resistance, which is something that we assumed in this experiment. And so additional data manipulation would need to take place to account for this. And as for the ammeter itself, it would show a lower current reading because of this higher resistance. And then what if we used a real battery? The time interval between 0 and the full charge would be almost instantaneous, but it wouldn't be 0 because, again, we cannot be assuming that the resistance is 0. All right, thank you guys so much.